What's going on, guys? Hey, Devs here, and we're back with some more LeetCode, of course. Let me fix my hair a little bit. We're doing some binary trees today. This should be day 16 now. We're getting up there. I won't really be able to remember the days before too long. But we're doing a 2-for-1 today. I solved 2 problems. I thought they were fairly easy. But we're messing with some binary trees, as you can see. And this one is in order traversal. So they want us to, given a root of a binary tree, return the in-order traversal of its nodes values, and they want us to store them in a list and return that list. So, excuse me. So given the input root, and this is the binary tree stored as what's it called? As an array. But 1 doesn't have a left node, it's null, and then the right node's 2, and then 2 has a left node 3, and then they want us to return 1, 3, 2. So in order traversal is you go follow the left path as far as you can, you store that value. So if we kind of go down this way, go down, go down, go down, store this value, and then we come back, we store this value, and then we go down the right node, and then if right node has a left, we go down, we store this value, and then when we go back to the root, we store this value, and then we go down to the right tree, store this value, and then we go all the way back up, and then we'll store this value once we check the left node. And then from here we check this one. If 3 has a left node, we'd go down that path, but since it doesn't, we'll store this value, and then we'll go down and store this value, and then we won't store that value. We will actually. So in order traversal is you check if it's a binary search tree, then the values would be in order, right? But this isn't a binary search tree. This is just a binary tree. But in order would be you check, given a node, you check the left node, and then from there you check the left node, and then you would store 4. And then once we go back to the original node, we'd give that value, and then we check the right node. And then that node, if it has a left node, we go down that one. And then once we go back, we go that one. And so we go all the way back to the first one. First one, we've already checked the entire left tree. So then we return that one, then we check its right node. 3 doesn't have a left node, so we return 3, and then we go down the right node. This node has a left node, so we return that value, and then we'd go back to the original node. So we'd go 4, 2, so we go back, 6, go right, then left, and then 5, so we go back to this node, and then we go 7, so then we go to here, and then we go all the way back to 1, you see 1 is next, and then we go to 3, 3 doesn't have a left, so we go 3, and then we go 9, so we go to 8, and then we go to this left side. And the easiest way to, I'm not going to explain binary trees and recursion with binary trees, but recursive functions work very well with binary trees, because once you go down to one tree, this is a subset of a tree. So this is also a tree. And then just a blank node is a tree, and so on and so forth. So every time you make it farther in the tree, it's another tree, and then 5, 6, and 7 is a tree, and then 6 is just a tree. It's just a single node tree, right? So that's kind of the idea we want to have. So we want to create a list of integers, because this is what we're going to store our values in. We're just going to call it list, and this is going to be equal to a new linked list integers. Call the constructor. First thing we want to do is check if because given the next example, we're given a empty list, so we want to return an empty list, right? And then given the root of 1, we want to return that list. So the easiest way to do this is to see if root is equal to null. If it's equal to null, then we want to return list. And then from there, we want to check the left side first. So make sure it has a left side first. So we'll do root.left. If that does not equal null, then what we want to do is we want to set list.add all. And then we want to call the in order traversal. And then give it the root.left. Right. So given the first call, we called the function again inside of the function. So when it gets to the first node, it's going to see that it's not null. So it's not going to return anything. Then it's going to check if it has a second left node, which it does. It has 2. So then it's going to say dot add all in order traversal root dot left. So then it passes the 2 node as a subtree. So just imagine that this entire right side of the tree does not exist. And we're only looking at this left tree now. So then it will run the same function on here. So it will create a new linked list. It'll see if 2 is null. If since it's not, it checks if it has a left. And since it has a left, it's gonna do the list.add all in order traversal root.left. And then the left node is 4. So then it's going to call the function again with root.left. And then once 4 is in there, we want to see if it has a left node. Since it does not, we want to go ahead and add the current value, root.value. And then we check the right node. So right does not equal null. We want to list dot add in order traversal root dot. And then we want to at the end return the list. So what this is going to do is it is going to traverse. It's going to call this function. So there's the function, there's the stack, right? And the stack holds all your local variables and all the function calls you make. So on the stack, we will have our first call with the root node of, or we'll just put 1 here, with 1, right? And then this is going through the function, and it's going to see that it has a left node, so it's going to call the function again, and that function is going to be added on top. And that's going to call the root.left, and the root.left is 2. And then 2 is going to go through this function. Since it's calling it has 2 function calls right now on the stack. Then 2 is going to see that it has a left node, so then it's going to call in order traversal as well. And then so that creates another function on the stack, and this time it has 4. So but this time when 4 goes through it, it's going to have its own list, right? I'd probably do that somewhere else. So 4 has its own list that it created inside its own function, right? It's in order traversal function. 4 is going to see if it has a left node, but it doesn't because it equals null. So then it's going to add its own value, 4. And then it's going to see if it has a right node, and it doesn't, so 4 is the only value we have. So it's going to return its list to this function call for 2. So 4 gets taken off the stack, and 2 gets past the 4 list for this. So 2's list right now has a 4 in it, because it added all of the list elements into our list. So then it will, since it breaks out of this, right, after a function completes, it comes back to the next line that it's in, and then so it will add its own value, so 2. will be added inside of it. And then it'll see if 2 has a right node, which it does. So it has 5. So then it will add a function call with 5 in it. Then 5 will go into its own function, and it sees 5 has a left node. So then it will call this function again, or this statement again, and it will call the function one more time, and then it will add it onto the stack. And this has 6 inside of it. Once again, 6 does not have a left node, so it won't call the function again, but 6 has its own, it has its own list, right here, and it will add 6 inside of it. And then it will check if it has a right node, and it doesn't, so it returns the list. So the 6 gets returned all, that's about, the 6 gets returned all the way back to the 5 function, right? So 5 currently will be, it will get returned the 6 inside of it. And so now we can start building 5's list. So 5 has the list of 6 right now. That's awful. 6 has the value of 6, and then it breaks out of this statement, breaks out of the if statement, and then it goes to the list.add its own value. So then 5 would be added inside of here. And then the it will also check if 5 has a right node, and it does. So then it creates another function call, adding all of the values that the inner traversal gathers into the list itself. So 7 gets called. 7 doesn't have a left node, so it doesn't even go in the if statement. So then it adds its own list value right here. So list then adds a 7 inside of here. And then it'll see if it has a right node, and it doesn't. So 7 is the only value inside of 7's function calls list. So then it will return 7 to the function that called it, or to the, I guess the statement that called it. So 7 gets taken off the stack, and then we go back to 5, and then 5 gets passed this 7 value, right? And then since we're in here, list.addAll, everything inside of the list that got returned, which is just 7, will get added inside of here. And then since there's no more adds, it just returns the list. And then 6, 5, and 7 will get returned to the to call. Right. So then this gets, we'll just do a, it's 6, and then a 5, and then a 7. And this entire list right here will get added onto our current list, right? So then the list that we've been building in the to function call will be 6, then 5, and then 7. And since there's nothing else to add, it will close this off, and then it will return this list right here to the first function call. So now we're all the way back to our original function call. And now 1 will start building its list since it finally called its first .add, and it added 4, 2, 6, 5, 7, and it's also right here on its in its function. And then it will do the list.add, and it adds 1 to the list, and then it will add all the values on the right side. So then it gets added onto the function call with 3. 3 sees if it has any left nodes, and it doesn't. So then 3 builds its own list, right? And adds its value. And then it sees if it has a right node, which it does. So it will call the function again with the 8 node. So then 8 is in here. It'll see if 8 has a left value, which it does. So then it will call its own function call with the 9 value. 9 will see if it has a left node. It does not. So it will add its own value inside. So now 9 will add 9. Then we'll see if 9 has a right node, which it does not, as you can see here. So then it just returns 9 to the previous function that called it. And so 8 now has the 9 value inside of here. So 8 will finally start building its list. It will add the 9, then it breaks out of the left node check, and then it goes to the adding its own value. It will see if 8 has a right node, which it does not, so then it will return this list to the previous function call, right? It's just like all the ones before it. And then 3 will get past the values 9, 8, right? And then it will add those to the list. So then 9 and 8. And since that's it, it will return this list to the function that called it. And now 1 gets past the 9/8 or the 398 list, and that will get added on to the end. So 398. 1 finally breaks out of its right node and then returns its own list. And nothing was before this function call 1, so then it will return this list here. And if you look here, it goes 4. There's 4, 2 and 2, 6 and 6, 5 and 5, 7 and 7, then 1 and 1, 3 and 3, 9 and 9, 8 and 8. So that will build our list the way we want it in the correct order and return it for all values. And we go ahead and make sure this solution works, as long as I didn't forget any semicolons this time. There we go. It runs for all the cases. So given 1, 2, 3, we'll want to return 1, 3, 2. And given the next one, and if it's empty, we just return an empty list. If it's one value, we just return the one value. Submit this and see how it does fares against other solutions. And it runs in 0 milliseconds, beats 100%. And yeah, that's kind of a brief overview for binary trees. Now, I don't know if my explanation was the best, but it was definitely an explanation. And then we're going to do the maximum depth. Yeah. This one. Maximum depth of a binary tree. So maximum depth, this returns, we're going to check a few things. I'm pretty sure I solved a different problem. This minimum depth. Yeah. Maybe I didn't submit it. No. Okay, we're just gonna do the max depth. I think it's the same. I think we're doing the max depth problem on the minimum depth. But for this one, we kind of want to do the same. We're going to create a stack, and we're going to see which value is greater or equal to, right? So we'll see, we'll make sure root, if root equals null, or return 0. I don't know if it has a null. Return its maximum depth, minus the longest node, farther to the leaf node, the number of nodes in the tree is a range of 0. Yeah. So if it's if there's not a node in the tree, the depth is 0. And other than that, we want to see if it has a left node. If root.left equals null, it does not equal null. We want to go ahead and store the int. So we'll create a int left and right. And then we want to go ahead and get the left's length. So left's length is equal to max depth of the root dot left. And if right dot or root dot right does not equal null, we'll go ahead and get the right value as well. So max depth of the right side, root dot right. And then after we have both those values, we want to see if, well, we can go ahead and check if root dot right is equal to null, and if root dot left is equal to null. Or, well, we can get rid of both of these actually. Well, no, we still need to check with those values. Don't mind me, it's just debugging some. So if both of those equal null, we want to return 1. Because the max depth of a singular node is 1, right? So we'll return that to a previous call or to just this call, right? And then once we get the right and left values, we want to check if right is greater than left. If it is, we want to return plus 1. And then else we'll return left plus 1. Because if they're equal to each other, it doesn't matter which one we return, so we'll just return the left plus 1. And don't forget the semicolons. I've been programming in Go all day, so I've been forgetting my semicolons for sure. And we can run this and see how that fares up against if initialized for that to 0, that to 0. Because if it doesn't have a right node, then it'd be 0. And, yeah. I'm gonna put these on separate lines, just because I don't like initializing the same values on the same line because it's kind of hard to read. You might miss one. And case 1 and case 2 both work. We can go ahead and return this. Submit this and see how it fares. Yep, 0 milliseconds beats all the cases. So what we're doing here is it's another recursive function call. So if the first node we get is null, we'll return 0, and that's fine. And then we'll see if the root if it has a left node, we want to get its max depth. And if it doesn't, the left will still be 0. So the right node should have at least a value of 1. And then yeah. And then we'll be returning the right side. So if you imagine 3, we see that the right side would be 1 and then 2. So right would give us 2, and left would give us 1. And then so we want to see which one's greater, which is 2. And then we'll return the 2 plus 1, because this node needs to be added, and gives us a value of 3. And then as you can see, I'm pretty sure it wants us to return 3. And that's kind of the logic here. Just another recursive call. We want to check each side's length. If it has it, if it has no length, we'll just return 1, because that means we're at the end of a list. This one doesn't have a left or a right node, but its value would be 1, and we return that to this call. And then both of these would return a value of 1. And then 2 would see which one's greater. It doesn't really matter, so it would return 1 plus 1. And this goes back to 3. So 3 would check 2, like I said, against this one would be 1, so it would return 1. And it would see which one's greater. 2 is greater, so it would return 2 plus 1, counting its own node as the height. So we got a 2 for 1 problem today. Those weren't too bad. It's a little bit of recursive calls. Recursive functions are kind of messy sometimes if you don't know how to do them properly. But the main thing with recursive functions is you want to recursively call it for each case, and then you want to have a case where you return, no, you don't return, well, you want to have a case where you return the, yeah, you want to have a case where you don't call the function. And in our example, if it has a left node, then it will call it, and if it has a right node, it will call the function again. And so this one will call the function 2 times, and this one will call it 0 times, since it has both nodes. So this one is for sure to return a value for its function call. So like each side has one call, and so the call will return, and it will return the value 1, like I said. But this one, it will also call it 2 times. So each function is calling it 1 time, and we want to return its max depth. So the case where the function doesn't get called is if it doesn't have a left and a right node, and we know that is the case for all binary trees. Given the Fibonacci sequence, you would return the function call itself. And well, we can go ahead and do the minimum problem too. Where's the minimum depth of binary tree? It's the same logic. So we have a left and a right. We want to get the size of both. And then if one is less than the other, we want to return it plus 1. And then if they're the same size, or the right is less than, we want to return right plus 1. Oh, min depth. Change the function calls, of course. That should work for both the test cases we got wrong. So given it's because we set left and right equal to 0. So 1 is always going to be 0. Think of how to handle that. Problem here is left and right is always 0. So if it has if it has one side and it has like 2, then it'll always return. What's the 10 to the 5th? I mean, we can set these to 10,000. If we set these to a really big number, then it will always pick the less. Yeah, as you can see here. I'm trying to think. So we can set both these. We can set both these equal to 0. And we can see that does not. That is not equal 0. Let's see. Left is not equal 0. That. Yeah, that should work. Because if left is 0, then it will return right. But if right and left are equal to 0, then it will just return 1 up here because it means that neither of them had a minimum depth. Because at the very least, right should be 1 or left should be 1, right? And then if both are 0, then it should return 1 and 2. Return the 1. It should be 1 plus 1 divided 0. Left. I feel like there's a better way to do this than just setting both these to abnormal large values. But we should, I mean, we can just do that. I think 10 to the 5 is just that. I'm gonna run this. I think it should pass, yeah, all the test cases. I was running 3 milliseconds. So our solution works exactly the same if you just switch right and left around and then set these to abnormally large values, larger than the max like depth of the tree. Yeah, I'm not too sad with that. I do want to see what the other solutions are. Depth first search, breadth first search. Both approaches. My 4-line Java solution. If you're using that, and thus use mid depth. Okay. Return. If either of those are equal to 0. Now, this is a very elegant solution. Because if either of them are 0, then mine does a lot of checks it doesn't need to do. I bet the max is fairly similar. But I'm not sad with these. They definitely could be concise down, fixed a little bit, but like I said, this is why we're doing it, to learn. And I haven't done much with binary trees in about 2 years. About the same time I did linked list, we went over binary trees slightly. And at the end we went over recursion and how to work with recursion. But anyways, I am going to call this quits. I've been recording, I think, for like 30 minutes now, maybe more. But we got 3 problems in today. All of them dealt with recursion and traversing the list. I hope you all have a good one. I think I got to do a little bit more homework and then probably hit the hay. But y'all stay blessed, stay healthy, and Hey Debs is out.